With all that in mind, let's see how the neural network is constructed. If you're familiar with the Keras Functional API, that's what we're going to be using here. Not too different from a normal deep neural network, right? We feed in the state information as our input, and then predict the Q value for each action as our output. Here's a little trick to speed up our training. We'll have another input that is the same size as our Q value layer. It represents which actions we want to evaluate. So imagine a vector where each index corresponds to an action. Each cell will have a 1 if we want to evaluate that action, and 0 otherwise. Then, we'll multiply that vector with the Q value layer to specify which node we want to activate. For backpropagation, we'll have zeros everywhere except for a 1, corresponding to the action that we took and the memory we're training on. Instead, for predicting, we'll give everything a 1 because we want to compare the Q values of all the actions and select the maximum. While we're at it, let's update our agent's act function as well. The first big difference is we'll have the agent act randomly until we have enough memories in our buffer to fill a training batch. Then, we'll also introduce something called random decay. This is to emulate the idea of the agent getting more confident in its choices. The more confident we are, the less randomly we'll act. There's some pretty interesting research out there looking to measure the statistical confidence of a neural network, but since it's computationally costly, this random decay has been found to be pretty effective. When we're not acting randomly, before we can send the state to a neural network, Keras expects a batch, so we'll need to add a dimension. Then we'll make our prediction mask, which is an array of all ones, so we can get a Q value for each potential action. So, at the end, we can return the index of the action with the highest Q value. Okay, last giant block of code. This is where all the magic comes together. First things first, we're going to pull out a batch of state transitions from the memory buffer. I skipped some data processing here. The result is we'll have 5 vectors of the same length, each corresponding to a column of our memory buffer. This will allow us to do vectorized math on these values, which will dramatically reduce our computation time. Next, we'll get the Q values of our state primes. We'll give our Q network our state prime batch and a corresponding action mask of all ones. This will give us a Q value for each action for state prime, which we can take the maximum value for. And now that we have the maximum value for state prime, we can calculate our label, which we'll call target Qs. Since there are no future states for when the game is complete, we'll take advantage of TensorFlow's where function to replace all the Q values corresponding to the end of the game with just the reward. Otherwise, we might accidentally over or undervalue the end of the game. Before we fit our labels to our states, we'll one-hot encode the actions that we took in each state. That will get us the training mask that will help our training be more efficient. Finally, since we're providing our own batch, we'll use the Keras train-on-batch function as opposed to the fit function. Fit does the batching for us, which is great for supervised learning, but here, we need the extra customization. Phew, that was certainly a lot. As we've learned from our agents, the best way to master this is to get our hands dirty and experiment. If it's not clicking yet, don't worry. Fire up that curiosity and don't be afraid to break things while going through the lab. Keep at it, and eventually you'll master the environment.